Hello all. In this video I want to go over the alkane and cycloalkane boiling point trends. Knowing these trends will be useful when we're asked to order maybe 3 or 4 molecules from lowest boiling point to highest boiling point. I would first like to interpret this graph, and then after interpreting the graph we should try to explain why these compounds fall where they do on the graph. But actually, I want to focus first real briefly on this idea of boiling point. And let me write down 1 or 2 concepts about boiling point that would be useful to know. First, the more intermolecular attractions a molecule has with other molecules, and the stronger intermolecular forces, you might know this as IMFs from general chemistry. The stronger those forces are, the higher the boiling point is. And we can also apply this concept to melting point. So the stronger the intermolecular forces are for a liquid, the higher the boiling point. And for a solid, if you have a lot of intermolecular forces, then the melting point for a solid is increased as well. We're really looking at forces that have molecules stick together, right? To either make a liquid or solid. Number 2, since alkanes, and we are only focused on alkanes right now, and cycloalkanes, but those are nonpolar. So what are the forces? Because there are no permanent dipoles. Well, since alkanes are nonpolar, the main IMF, you might recall, in making molecules stick together is London forces. And I like to think of London forces also as induced dipoles. Not permanent dipoles, because we have no electronegative atoms in these molecules, but induced dipoles. We'll talk more about the reasoning behind these 2 bullet points, but now's a good opportunity to look at the graph. Let's look at the 7-carbon line, which is here. And so we are focused on this blue dot here, red dot here, and the green dot. So I'll circle those 3. Okay. The blue represents molecules that are 2-methyl branched alkanes. I believe the 7 means the total number of carbons. So if there is a methyl branch, then that blue dot here is 6 carbons in a row, and a methyl at 7. Do you see how that satisfies this definition? On the blue line, these are molecules that have a methyl at carbon number 2, but I'm interested in the molecule that has a total of 7 carbons. Now, this red dot, which has a higher boiling point, is what? The red is unbranched alkane. Okay, a 7-carbon unbranched alkane. 1, 2, 3, 4, 5, 6, and 7. It's telling me that this molecule has a higher boiling point than this one. And if we just read it off the graph, this is 100 degrees degrees Celsius. That's the boiling point. And for the blue one, trace it. We'll call it 88, 90. We'll say 88. The green, unsubstituted cycloalkane. Okay, maybe you're pretty good at drawing now hexagons, but I have a 7-carbon ring, 7-carbon cycloalkane. That is a little bit trickier to draw. Make a shallow roof, have these slanted walls, and then go to the floor like that. That should be 7 carbons. Start from the top. 1, 2, 3, 4, 5, 6, 7. And look at its boiling point. It's about 100, maybe 18. Is that right? 118. So ring molecules with the same number of carbons tend to be higher, have a higher boiling point. Now, let me write down 1 more bullet point, and then we will look specifically at these trends between branched, linear, and cyclic. But there's 1 more bullet point I want us to look at. the third bullet point is the bigger the molecule, the more London forces it has, and the more London forces it has, the higher the boiling point. Okay, I have a small molecule, medium size, and bigger. And look at the phase. Ethane, 2-carbon chain, is a gas, low boiling point, right? Gases have low boiling points. But when we increase it to 8 carbons in a row, okay, we have more London forces, and you want to think of it as maybe something like this, right? You have molecules kind of sticking to each other because these induced dipoles, just by the random movement of electrons, let's say that carbon is partial negative. Well, that will render a carbon nearby in a different molecule partial positive. And so the more opportunities you have for induced dipole interactions, the higher the boiling point. And that's why octane is a liquid, definitely a higher boiling point than the gas. And now if we increase it to 20 carbons, a 20-carbon alkane, that is actually the structure for wax on a fruit, like apple wax, natural apple wax. And that's solid, right? It's not a liquid. So that has even a higher boiling point. And we can even think of these as melting point, like when does this octane freeze, right? That's the same as the melting point, a very, very low temperature, where this one is solid at room temperature. So its melting point is higher than room temperature. So we can even put here melting point. But really for alkanes, we're really more concerned about boiling point. Okay? Now, these all have the same number of carbons, 7 carbons. And so how do we explain these trends? Do they really have, is there a rationale that the boiling point trend is in this direction? And honestly, I forgot one more. Yeah, I definitely forgot one more bullet point. Let me add that right now. Well, what I really meant to add to this bullet point is the bigger the molecule, the more surface area it has. And so I kind of described it here. There's a lot of surface area contact between these two molecules. And the more surface area you have, the more chances you have for London forces. The more London forces you have, the stickier the molecules are, the higher the boiling point. And so the important part as we move forward in this is that do these molecules really have a difference in surface area? Let me try to prove that to you, but I think for me it's easier to look at the 5-carbon examples. You'll see why in just a bit. So if we have, let's compare, we already compared size, but what if we have 2 molecules that have the same number of carbons? One is linear, and one is branched. Okay, they both have 5 carbons. In this case, if we look at our chart, the linear has a higher boiling point than the branched. Why is that the case? Let's put our trend, and let's say this linear, and this is branched. Okay, it's because the branched overall shape is spherical. And this is well, it's linear. Okay, and the analogy that I like to think about is if you have spaghetti and meatballs on a plate. Let's draw our plate here. If you think about the meatballs that are spherical, right, they have very little surface area contact with each other. Okay, but when you think of the spaghetti, they have a lot of surface area contact with each other. Okay, so as you're walking down, walking in your kitchen with a plate of spaghetti, which is more likely to roll off the plate? It's the meatballs. It doesn't take a lot of energy to separate. Maybe that's the better point. So these spherical molecules, not a lot of energy needed. to separate. That's the idea of boiling, right? You're separating the molecules to get them into a gas. I forgot totally how to spell separate. That doesn't look right at all. I think it's an E. That doesn't look right either. Anyway, so spherical molecules have less surface area contact with each other, which means that if you extend that thinking, linear has a higher boiling point than branched. It takes more energy. It takes more energy to separate linear molecules than branched molecules. Okay. Now, what about this trend? Okay, same number of carbons, but now we have cyclic. Well, this trend tells me the cyclic is going to win the higher boiling point. So let's stick with 5 carbons still. And we have the pentagon has a higher boiling point than the linear. The way I like to think about this is I like to think about these cyclic molecules as dinner plates. Dinner plates. And we still have spaghetti. But, you know, dinner plates can stack. Dinner plates can be on top of each other. And there's a lot of surface area contact. Surface area contact. And that's why cyclic molecules have a higher boiling point than linear molecules that have the same number of carbons. That explains these 3 molecules, right? Cyclic is the highest boiling point, then linear, and then branched. We have the dinner plate, spaghetti, meatball. And the reason why I like to use the 5 carbon example is that this looks more spherical when you have branching on a 5 carbon alkane.